We've all heard of Einstein, and many of us have heard of his general theory of relativity. But the question is, do we actually understand what it means? Scientists today are still trying to completely understand Einstein's field equations, but I bet that in 5 minutes we can gain a basic and insightful understanding on this truly groundbreaking topic. To start, we're going to break down this statement, general theory of relativity. The first part, the general theory, simply states that something accepted and useful in the physics world, and also big or general in consequence. Now, relativity tells us basically how this theory is applied. That is, it's relative to something else. If you think about it, everything is relative. For example, if you're waiting at a bus stop and see cars passing by, they are moving relative to you. However, if you're in a car and see someone at a bus stop, then they are the ones that appear to be moving. Position, motion, acceleration, etc. They're all relative to the observer. And if you change where you're making your observations from, or your frame of reference, then different things appear to be in motion. The Earth, the other planets, the Sun, the galaxy, they're all in motion depending on where you place your frame of reference. Awesome, we now understand that we're talking about a major theory that's relatively applied. So now before we dive into general relativity, we're going to gain a better understanding of its development by first taking a look at special relativity. Special relativity was posed by Einstein 10 years prior to general relativity. And it's the theory where we get equals mc squared, which basically describes the relationship between mass and energy and is used often in quantum and particle physics. Special relativity itself has two postulates. The first is that the laws of physics are the same in all inertial frames of reference, that is, frames of reference that are moving at constant speeds. The second is that the speed of light is constant for all observers, meaning that light travels independent of the speed of the observer. For example, let's imagine a spaceship traveling at half the speed of light fires a laser beam from the front of the ship. You might think that the speed of the laser would be 1.5 times the speed of light. However, as we said before, nothing can travel faster than the speed of light. So Einstein determined using the equation speed equals distance over time, that for the speed of light to remain the same, both distance and time would have to shift, which happens in what we call length contraction and time dilation. To see how this relates to general relativity, let's take the concept that space-time, the interwoven fabric of the four-dimensional universe, can be stretched, bent, and manipulated as shown in the previous example. This concept proved to be the very basis upon which Einstein formulated his general theory of relativity. This and one other very important idea, the equivalence principle. The equivalence principle, simply stated, shows the equivalence of the gravitational force and the force experienced in accelerated frames of reference, or non-inertial frames. Let me explain. Say you're standing in an elevator and you take a ball out of your pocket. You let go and watch it drop to the floor. If I were to ask where you are, you'd probably assume you're at rest on Earth. However, you could also be inside an elevator in space that has a constant acceleration, therefore causing the appearance of gravity. Say you're in an elevator again, but this time you aren't touching the ground. And when you pull a ball out of your pocket and let go, it goes nowhere. Now you may be thinking, aha, I'm in space. But Einstein again proposed another option. You could be on Earth in free fall with the elevator, having a constant acceleration and therefore causing the appearance of weightlessness. Fitting these two pieces of the puzzle together, both space-time and the equivalence principle, took a lot of complex math and reasoning. But after about a decade, Einstein finally cracked the code with his 10 equations of general relativity. As a side note, even though this looks like it's one equation, it's actually 10 because it involves some crazy tensor calculus, matrices, and other insane math. And so now the question is, what does this equation mean? Well, it basically describes very specifically how mass and energy and momentum and pressure are distributed throughout the universe, as well as how they bend space-time. It is this curvature of space-time that then influences how mass, energy, etc. are spread. In short, to quote one of Einstein's later colleagues, John Wheeler, space-time tells matter how to move, matter tells space-time how to curve. The results of such a discovery are incredible. First of all, which we call gravity, is actually the result of the Earth bending space-time, and it's the same reason that the Earth orbits the Sun. Other implications of this theory is that it predicted black holes and gravitational waves many, many years before they were discovered. It also permits the existence of wormholes and the theoretical possibility of time travel. Einstein's general theory of relativity truly was an incredible breakthrough, arguably one of the most monumental in all the history of modern science. These equations are genius, and now that you have a basic, well-built foundation of them, what does that make you? New parts of his theories are still being discovered and explained, and it's evident that his equations still contain many secrets to the universe. Now that you have gained a basic understanding of some of Einstein's greatest life work in only 5 minutes, the question is, what's next? That is up to you, but equipped with your knowledge of the universe, the possibilities are endless.